Hello everyone, I hope you all are doing well. Today we are going to cover a few very important circle theorems. Let's start with this one. Subtended angles in the same segment of a circle are equal. To understand this theorem, let's draw a circle first. This is a circle with center A and we have drawn a chord DC. Now through this chord we are subtending angles at some points on the circumference of the circle. Here I have taken points E, F, G, B, H, and you can see we have subtended angles. For that we have just joined ending points of the chord D and C with these points. Now as per the theorem, these all angles CED, CFD, CGD and so CHD. These all angles should be equal because they belong to the same segment of the circle. Segment, I hope you can recall. Any chord of a circle divides it into two segments. Here this green chord DC is dividing the circle into two parts or sections. These sections or areas are called segments. Here the segment containing red lines is the major segment and the segment containing grey lines is called the minor segment because of its sizes. Let's take 3 points in minor segment also, KIM, and join these points with the endpoints of chord DC. So here you can see in the major segment every angle is 61.5. That means they should be exactly equal to one another because they all belong to one segment, that is major segment of the circle. Similarly, if we see the angles of minor segments, that is angles CID, CKD and CMD, and as per this theorem, they should also be equal to one another because they all belong to minor segment of the circle. So if we measure any one angle out of these, or if we know any one out of them, then we can easily understand that remaining angles would also be same. Now see, I have removed this chord CD. Then also this theorem holds good. The reason you can simply understand with the logic. In these subtended angles, this complete chord DC is not playing any role, but only the endpoints of this chord DC, right? Because for segment also, what exactly we need? Just the two endpoints. That is why generally in questions are like this. And to apply this theorem, we search for the chord. But basically there is no requirement of the chord. What all we need is the endpoints. Because through endpoints also we can recognize that the angles belong to same segment or not. Here you can see in minor segment also, all the angles are equal to one another. If one is 108.5, then remaining two will also be same. Even if there is absence of chord, because we have endpoints through which we can easily understand that red ones are in major segment and grey ones are in minor segment. So if you see questions in this form also, then also please understand that if we have endpoints, then that is enough for the application of this theorem. Now let's move on to another theorem. The angle subtended by an arc at the center is double the angle subtended by it at any point of the remaining part of the circle. For that again we have taken a circle with center A. Again if we take arc or a chord to subtend angle, that is the same thing, because ultimately what we need is endpoints D and C. So I have subtended two angles here, A at the center and E at the circumference of the circle. So according to theorem, if A is 88.2 exactly, then the angle CED should be exactly half of it. Here if we subtend one more angle at the circumference, then even from the first theorem of the video, you can understand that angle B would be equal to angle E because they both belong to same segment of the circle. Or you can do it again by this theorem also, just dividing 88.2 by 2 and then you will be getting the value of angle B. Here also if the endpoints are given and chord DC is not given, then also it doesn't matter because the theorem holds good even if in the form of arc DC. But the only condition is that both the angles, the center one and the circumference one, should be in the same segment of the circle. Let's move on to another theorem of the circle. Angle subtended by a diameter or semicircle at any point of the circle is 90 degree. This is actually the sub-theorem of the theorem which we have done just now. Here we have taken the largest chord of the circle, which is a diameter DC, and we are subtending angles at E, F and B. Angle DAC is 180 because it's a line. So angle subtended by DC at the circumference would be just half of 180, that is 90 degree. So E, F and B all would be 90 degree each. So we can say that we have subtended angles through diameter, which is the largest chord of the circle, or by the semicircle DC. Now next move on to another theorem of the circle. For that, first understand what is a cyclic quadrilateral. And all the vertices of the quadrilateral lying on the circumference of the circle, it is called a cyclic quadrilateral. Let's draw a cyclic quadrilateral first, then we will move on to the theorem. So here we have drawn a quadrilateral within the circle. This type of circle is called circumscribed circle, which contains a cyclic polygon inside it. So you can draw any quadrilateral within the circle. We have taken two quadrilateral within the circle. Now let's move on to the theorem. It says that in cyclic quadrilateral, the sum of either pair of opposite angles is supplementary. Supplementary means sum of the angles is equal to 180. That means if I quote these angles of cyclic quadrilateral, then we can find out the value of opposite pair by subtracting from 180 degree. Like angle F is 91.6, then we can find out angle D by 180 minus 91.6 in quadrilateral EDCF. Similarly, in another quadrilateral IBHG, angle I is given 89.5, then opposite pair angle would be 180 minus 89.5, that is 90.5 degree. This way you can find out all the remaining angles of a cyclic quadrilateral. But the condition is only that it should be a cyclic quadrilateral, not a quadrilateral only. For example, let's take this circle and I have drawn this quadrilateral. This is a quadrilateral CDEG, but it is not a cyclic quadrilateral because the vertex G is not on the circumference of the circle. Then this theorem does not hold good. Now, if I put this point on the circumference of the circle, now this is a cyclic quadrilateral. That means positioning of all the vertices is very important. All the vertices should be on the circumference of the circle. Even if one point is not there on the circumference of the circle, then we cannot apply the cyclic quadrilateral theorem on this quadrilateral. Now look at the next theorem. The tangent at any point of the circle is perpendicular to the radius through the point of contact. Let's say this is a circle with center A, and to draw a tangent we have taken a point B. Through B this is a tangent. So our theorem says that if you join this radius through joining the points A, B, then angle B is 90 degree. Now the next theorem. The length of two tangents from a common external point are equal. For this, we have taken an external point C through which we have drawn two tangents CB and CD. Then according to theorem, length of CB and CD would be same. Also, if we join point C with the center A of the circle, then AC divides the angle BCD into two equal parts. We can say this line AC is the angle bisector for this angle BCD. So depending upon the question asked, whether it is for angles or length, we will be applying this theorem. I hope this video was helpful for you. Thank you so much for watching. Bye-bye.